In this video, we'll dive into the design of a visual search system, a common and powerful machine learning application used in e-commerce, social media, and content platforms. A visual search system allows users to upload an image and retrieve other images that are visually similar. Whether it's finding a matching pair of shoes, identifying a piece of furniture, or discovering related art, visual search brings the convenience of search by image to real-world problems. We'll break down the components of such a system, from problem definition and requirement clarification to data preparation, model training, and deployment in production. You'll learn not just how to build the model, but how to frame the problem correctly and serve it at scale. Let's get started with the problem statement. A visual search system helps users discover images that are visually similar to an input image. Here are some good questions to ask in the requirement clarification phase. Shall we rank the results based on similarity? Shall we support videos? Are the results personalized to the user? Do the images have metadata that we can use? What's the SLA? In a visual search system, representation learning is at the core. It's how we make images understandable and comparable to a machine. 1. Transforming images into embeddings. The first step is to use a deep neural network, typically a convolutional neural network, CNN, or a vision transformer, to convert an image into a compact vector representation, also called an embedding. These embeddings are high-dimensional numerical vectors that capture semantic information about the image. For example, different views of the same sneaker should map to similar embeddings, even if the colors or lighting conditions vary. The goal is to encode the image in such a way that its content and meaning, not just raw pixels, are preserved in the vector. 2. Closeness in embedding space reflects visual similarity. Once we have embeddings, we define a similarity metric, like cosine similarity or Euclidean distance, in that space. Visually or semantically similar images will have embeddings that are close together. For example, a red handbag and a pink handbag may differ slightly in color, but will still be close in the embedding space because they share structure and category. This enables powerful capabilities like cross-domain retrieval, sketch to photo, duplicate detection, cluster-based categorization. This is how the system understands what images mean, not just what they look like in pixels. 3. Ranking by similarity scores. During retrieval, we compute the similarity score between a query image and all indexed images. These scores are used to rank results. Higher scores indicate higher similarity. For example, in a shopping app, uploading a photo of a shoe returns similar-looking shoes sorted by visual proximity. This ranking allows users to find the same product in different styles, discover related items visually, e.g., fashion, furniture, get personalized recommendations based on image-based preferences. Ultimately, representation learning enables the entire search by image experience by turning pixels into semantically meaningful and rankable results. In visual search systems, data preparation isn't just about images. It also includes understanding user behavior and how users interact with those images. We'll break it down into two key areas: data engineering and feature engineering. 1. Data engineering: images, users, and user-image interactions. Images. This is our core input. We collect high-quality product or content images, clean, well-lit, and representative. These can come from internal catalogs, user uploads, or curated datasets. Users. Information about users can help personalize results or re-rank based on preferences. This might include user profiles, search history, session behavior, or device type. User image interactions. Extremely valuable for self-supervised or contrastive learning. Examples: clicks, likes, views, add to cart events. Which images users searched for and what they eventually selected. These signals help us to find positive and negative pairs for training a model to learn similarity. So, even though this is a visual system, user behavior gives us semantic grounding for what similar means in practice. 2. Feature engineering, all about images. At this stage, we focus on transforming raw images into a form the model can learn from. Raw pixel input. Images are resized, normalized, and possibly cropped or padded. Often, we use pre-trained CNNs, like ResNet, EfficientNet, or Vision Transformers to extract deep features. Data augmentations. Flip, rotate, color jitter, zoom. This helps the model learn invariants to common image changes. Additional image metadata. For supervised models, we might also use image categories, e.g., sneakers, dining table, color labels, style descriptors, brand tags. These help enrich the representation during training or can be used in multitask learning setups. In short, all features are visually grounded, but they may also include semantic overlays to improve the robustness of our embeddings. Effective visual search starts with a solid understanding of both what the image is and how users interact with it. That's what this data preparation phase is all about, setting up the foundation to learn meaningful, user-aligned visual representations. Once we've prepared our image and interaction data, the next step is choosing the right model architecture. In a visual search system, the model's job is to convert images into meaningful embeddings, and this is where neural networks shine. 1. CNN-based architectures. Convolutional neural networks, CNNs, have been the traditional workhorse of visual tasks. Examples: ResNet, EfficientNet, Inception, MobileNet. CNNs are good at capturing local patterns like edges, textures, and object parts. They're efficient and well-optimized, especially for mobile or latency-sensitive use cases. CNNs are especially strong if you're working with relatively simple or well-aligned images like e-commerce product photos. These are a strong default choice and are often pre-trained on ImageNet for faster convergence. 2. Transformer-based architectures. More recently, Vision Transformers, VITs, have gained popularity. Examples: VIT, Swin Transformer, DIT. Transformers use self-attention mechanisms to model global context, not just local features. This can be particularly powerful for scenes with multiple objects, fashion search, where layout and interaction between items matters, matching user-uploaded images to catalog items. Transformers typically need more data and compute, but can outperform CNNs on complex visual reasoning tasks. 3. Hyperparameters to tune. Number of convolutional layers. Controls depth of feature extraction. Deeper models can capture higher-level semantics, but may overfit or slow down inference. Number of neurons per layer. Affects model capacity. Too few may underfit. Too many can lead to slow training and overfitting. Size of the embedding vector. The embedding is the final output used for comparing images. Typical sizes range from 128 to 512 dimensions. Higher dimensional embeddings may capture more nuance, but can also increase storage and slow down similarity search, e.g., in face or ANN indices. These hyperparameters should be tuned with respect to your latency budget, retrieval precision, and hardware constraints. Ultimately, choosing between CNNs and transformers and tuning your architecture depends on your domain, your data, and your performance constraints. It's often best to start simple, e.g., ResNet, and iterate based on retrieval quality and deployment feasibility. Now that we've selected a model architecture, we move into training. Specifically, training a model to embed images so that visually or semantically similar images are close together in the embedding space. We do this using contrastive training. 1. Contrastive training. Learn by comparison. The main idea behind contrastive training is to teach the model what makes two images similar or different. Rather than predicting a label, like in classification, the model learns to pull similar images closer in the embedding space and push to similar ones apart. This is critical in visual search, where we care more about relative similarity than about absolute categories. 2. Training dataset structure. For each training example, we construct a triplet: query image, the anchor; positive image, visually or semantically similar to the query; N-1, negative images, dissimilar distractor images. This can also be structured as N-way classification, where the model is trained to pick the most similar image among N candidates. The contrastive setup teaches the model discrimination. It must identify subtle differences and common patterns across images. 3. Labeling, getting positive and negative pairs. Human judgment. Curated datasets with human-labeled pairs, e.g., same product, same scene. Expensive, but high quality. User interactions, weak supervision. Use implicit feedback like clicks, dwell time, purchases. For example, if a user searches by image and clicks a result, that pair is likely similar. Self-supervision. Create positives by augmenting the query image, e.g., crop, rotate, color jitter. Common in SimCLR Moco, BYL style setups. Scalable and doesn't require labeling. These different methods can be mixed for better coverage and robustness. 4. Loss function, contrastive loss. We use contrastive loss, or variants like InfoNCE or triplet loss, to train the model to output high similarity for positive pairs and low similarity for negatives. Similarity computation, usually via dot product or cosine similarity between embeddings. Softmax layer converts the similarity scores into probabilities over the N candidates. Cross-entropy loss measures how well the model assigns high probability to the correct, positive image. Encourages the model to be confident and correct in ranking similar images. The better the loss is minimized, the more meaningful and compact your embedding space becomes. Contrastive training is a powerful strategy in visual search. It teaches the model how to recognize visual similarity through experience, either human-labeled or derived from user behavior, and it directly optimizes for what we care about, retrieving the right image among many. After training the visual search model, we need to rigorously evaluate how well it performs, both offline during development and online in production. Evaluation helps us measure how good the image embeddings are at retrieving relevant results. 1. Offline metrics, evaluated on labeled test datasets. These metrics are computed without user interaction. They simulate how well the system retrieves relevant images given a query image. Mean reciprocal rank, MRR, looks at the rank position of the first relevant image. Higher MRR means relevant images are being ranked near the top. Recall at K and precision at K. Recall at K, out of all relevant images, how many are in the top K results? Precision at K, out of the top K results, how many are actually relevant? These are especially useful for e-commerce and product discovery. Mean average precision, MAP, averages the precision across multiple recall thresholds for each query. Captures both precision and ranking quality, often used in object detection and image retrieval tasks. Normalized discounted cumulative gain, and DCG, weights relevant results based on position. Higher ranking relevant images contribute more. Useful when relevance is graded, e.g., exact match versus similar style versus same color. Offline metrics give us an initial signal of how well the model performs before deployment. They're essential for model selection and iteration. 2. Online metrics, evaluated in production with real user interactions. Once deployed, we track how the model impacts actual users. Click-through rate, CTR, measures how often users click on search results. Higher CTR typically indicates that the search results are perceived as more relevant or attractive. A key signal for validating model updates and A/B tests. CTR is simple but powerful. It reflects real user satisfaction. If embedding changes improve offline metrics but hurt CTR, we may be optimizing for the wrong things. Combining offline metrics for development and online metrics for real-world performance helps ensure our visual search system is both technically sound and user-friendly. Always monitor both to make informed trade-offs. Once our visual search model is trained and evaluated, the next step is serving it in production so that users can actually use it. Serving involves building an efficient and scalable prediction and indexing pipeline. Let's break this down into two components: prediction pipeline and indexing pipeline. 1. Prediction pipeline. This pipeline handles real-time inference. That is, when a user uploads an image or clicks on one, how do we quickly return similar images? Embedding generation service. This service takes the query image, e.g., user upload or product image, and passes it through the trained neural network to produce an embedding vector. Must be fast and consistent with how training embeddings were generated, same model, pre-processing, etc. Nearest neighbor service. Once we have the embedding, we need to find the most similar embeddings in the image index. We use approximate nearest neighbor, ANN, algorithms like FASS, CNN, or Annoy to scale this search to millions of items while keeping latency low. Output is a list of candidate image IDs, usually ranked by similarity, e.g., cosine similarity. Re-ranking service. After retrieving candidates, this step applies business-level logic to reorder or filter results. Examples: filter out out-of-stock products, boost new arrivals or high-converting items, personalize based on user preferences or past behavior. This multi-step approach keeps retrieval fast and scalable while allowing post-processing flexibility. 2. Indexing pipeline. This pipeline prepares and maintains the image index used for similarity search. Index service. Pre-computes and stores embeddings for the entire product catalog or image collection. These embeddings are indexed using ANN structures optimized for fast retrieval. The index must be regularly updated to reflect new images or products, removed or deprecated items, model updates, which require re-embedding and re-indexing. A robust indexing pipeline ensures that what users search against is always up to date and consistent with the model. The serving system turns embeddings into real-time results. It balances model performance, latency, and business logic. A good serving architecture is critical to making visual search feel instant and relevant to end users. Once we've transformed an input image into an embedding, we need to find similar embeddings from our image index. This is the core of visual search. The challenge is, how do we do this quickly when we have millions of images? The key here is nearest neighbor search, which is also the subroutine of many other problems. 1. Exact nearest neighbor search. In exact search, we compute the similarity, like cosine or Euclidean distance, between the query and every single item in the index. This guarantees the most accurate results, but it's computationally expensive and doesn't scale well for large datasets. For real-time applications like visual search, this level of precision is often not necessary. Approximate methods give near-identical results at a fraction of the cost. So we turn to approximate nearest neighbor, ANN, methods. 2. Approximate nearest neighbor, ANN. ANN algorithms trade off a tiny bit of accuracy for massive speed and scalability. Let's go over 3 main categories. A. Tree-based ANN. Examples: KD trees, R trees, ball trees. These data structures organize the embedding space hierarchically. Efficient for low-dimensional embeddings, typically and LT, 50D. Less effective in high dimensions due to the curse of dimensionality, too many comparisons still needed. B. Locality-sensitive hashing, LSH. Hashes similar items into the same bucket with high probability. Distance between vectors is preserved through hashing. Offers sublinear query time and works well for high-dimensional data. Great when you need fast, low-latency lookups and don't mind occasional accuracy loss. C. Clustering-based ANN. Examples: IVF, inverted file index, in FAISS, HNSW, SCNN. Embeddings are first grouped into clusters. At query time, the model searches only within the closest clusters. These methods are currently state-of-the-art for large-scale ANN. Used by most production-grade visual search systems, e.g., Pinterest, Google Lens. These ANN methods allow us to serve image queries in tens of milliseconds, a key requirement for user-facing applications. Approximate nearest neighbor search is what makes visual search fast, scalable, and responsive. Choosing the right ANN method depends on your embedding dimensionality, latency constraints, and accuracy requirements.